The students and general seekers of truth. In this video, we are going to look at some application of antiderivatives with respect to some objects that are falling from the sky. And let's see here, an object is thrown directly upwards with a velocity of 20 meters per second from an initial height of 3. And the acceleration due to gravity is negative 9.8 meters per second squared. And we want to find the position function given the height of the object as a function of time. And just to recap things from what we know before, let's say that h of t is the position function, then the derivative of h would be equal to the velocity function. And the derivative of the velocity, or the second derivative of h, would be equal to the acceleration function. And now we're told that the acceleration is a constant negative 9.8 meters per second squared. So we want to work backwards, and we've got to find the position function in all of its detail. Well, let's work backwards. If we have acceleration and we want to find velocity, then we need to find the antiderivative of acceleration, which, not too difficult, is 9.8 t, okay, because we're doing this in terms of t, plus some constant. And normally we would say big C, but I'm going to use a more familiar notation, V naught, where V naught is some constant. Now, we want to figure out what V naught is equal to, so we're going to use the fact that it was launched at a velocity of 20. So that means V of 0 is equal to 20. So that means 20 is equal to negative 9.8 times 0. Okay, one time is equal to 0 plus V naught. So very simply, this goes away and we get that V naught is equal, in fact, to 20. So our velocity function, v of t, is equal to negative 9.8 t plus 20. Now let us continue and find the position function. We have the velocity function already, but in order to find the position function, we have to take the antiderivative of the velocity. So the antiderivative of the velocity function would be t squared times negative, so we're going to take this number here and divide it by 2. So we're going to get negative 4.9. Okay? Because if you were to take the derivative, you would be multiplying by 2. And then plus 20 t plus some other constant. But instead of using c, I'm going to use h naught as the initial height. Then we know that the initial height is equal to 3, so that means when time is equal to 0, then the height is in fact equal to 3. So we're going to set this up. 3 is equal to negative 4.9 t squared plus 20t plus h naught. Whoops, I'm sorry. T we already know is 0 because that's the initial height. That's the initial time, right? The time always starts at t equals 0. So this is 4.9 times 0 squared plus 20 times 0 plus h naught. So the zeros will cancel, and we get that 3 is equal to h naught. So our final answer for the position function is that h of t is equal to negative 4.9 t squared plus 20t plus 3. So this is the position function. If you've studied physics in any sort of serious sense at all, perhaps this equation will seem familiar to you. It's, at least for me, I know that this is just some equation out of a physics textbook that I memorized until I learned calculus, and this is the true origin of this function here. Of the position function is equal to negative 4.9 t squared plus v naught, the initial velocity, t, plus h naught, the initial position. So there you have it. We'll end this lesson here on a note that relates to something practical and in one of the more famous functions here in the history of physics and calculus. Thank you for watching. As always, remember to ask for help when you need it. Always seek the truth, and have a wonderful day.